Okay, thank you very much, Mark, first of all, for the invitation and, of course, also for the introduction, very kind introduction. So, this talk will be about this recent paper I put out in February. And I decided to focus a little bit less on the scattering amplitude part because I think for this audience, the IR jungle is a bit more interesting. I think there's a lot to learn on some of the technical aspects here, but of course, feel free to ask about the amplitudes part as well. With this out of the way, yeah, brief outline. So I want to first start with a short motivation, with an issue, with the issue that kind of motivated this paper for me, namely the limit k to 0. This has been bugging me for really a few years already, and I'm very happy that I finally understood what's going on there. With this kind of problem stated, I'll present a toy model, namely an approximation of the quartic scalar vertex, where the setup is so simple that we can learn something analytically, but still understand some of the momentum dependence that will be a key player in this. So let me dive right into it and discuss this limit k to 0, or really asking the question, what could possibly go wrong? So you probably all know the propaganda, maybe you're teaching it like this of the FRG. You sit down and compute beta functions in a truncation. You look for fixed points, you look for critic exponents, you perturb into relevant directions, you integrate down the flow down to k equals 0, and you read off the physics. Right, so very nice, very clean, nothing can go wrong ever. Well, not quite. I really want to focus on this step here, the integrating the flow down to k equals 0. Of course, in gravity, there are a bunch of other problems that I will not talk about today, including, diffeomorphism invariance and other problems. But really, I want to focus on this limit here. And as it turns out, there's quite some technical issue here. This may be a little bit unexpected. So what is this? It's really a kind of infrared divergence, but the bad kind. So this, I want to illustrate this with very specific example, the Gaussian term. But really, this problem arises for any coupling that has a negative mass dimension, maybe except for Newton's coupling. So for the sake of the argument, consider the Gaussian term. So g cubed, this has a mass dimension -2 times the y cubed. At the classical level, right? So if you would write down the classical FRG beta function of the dimensionless coupling, you first introduce a dimensionless coupling by, well, multiplying capital G3 by k squared. This combination is dimensionless. If you do not include quantum corrections, the beta function is very straightforward. It's just 2G3. And of course, you integrate this beta function again, you get back what you put in, namely G3 is proportional to k squared. The constant of proportionality is just a coupling in the infrared. Very simple. Good. So now you turn on quantum corrections. And I turn quantum corrections on just from Einstein-Hilbert. Okay. So you ask the question, maybe, what is the beta function of the Gaussian term if I introduce quantum corrections from an Einstein-Hilbert action? And as it turns out, to leading order, you will get a constant contribution to the beta function. They're higher order contributions, but they are not as important for the infrared as this constant term. Now you do the same analysis. So you have a beta function now with a constant and 2G3, which is just the canonical term, and you solve it, and you find, oh, the dimensionless coupling has a constant piece now in the infrared. There's, of course, still the k squared, but the kind of nasty bit is really this minus c over 2. Because now you want to define the dimension full quantity, right? You want to define the capital G3. And you see that, well, this diverges as k goes to 0, because you have to divide the dimensionless coupling by k squared. So this constant makes trouble. And this is kind of at the heart of the problem. This is really the problem that was bothering me for quite some time. and that I set out to understand in this paper. So really the physical limit is obstructed in this kind of scenarios. So this whole nice story of where we take the FRG, we integrate it down to k per 0, it's not as simple, unfortunately. Now, what can happen in some cases is some regulator choice can remove offending terms. So this happened, for example, for the Gaussian decoupling. You can find a regulator where the C does not appear. It's just 0 for this regulator choice. But this is not generic. So you can convince yourself that if you go higher in the heat kernel, look at other couplings, this will not happen anymore eventually. So this is really a generic problem that you're facing. This is what I just said. You can repeat this argument, and basically the heat kernel knows no mercy. You will get higher order terms, and you will not be able to set all these problematic threshold functions to 0. Good. So kind of the upshot of this, or what will resolve this issue is that the derivative expansion and the limit k to 0 do not commute in gravity. This is kind of what I'm working towards. And we'll see the details of why I'm making this statement. And then maybe we'll also see where you can trust the derivative expansion in gravity and where you would make a mistake. So this is kind of setting the stage or setting out a problem. And now we are moving to trying to solve this problem. And for this, I want to investigate the quartic scalar vertex in a momentum-dependent fashion. As it turns out, momentum dependence is one of the ways to solve this problem. Good. So for now, I want to just investigate gravity in the form of Einstein-Hilbert plus 2 massless scalars. And later we'll also discuss massive scalars for a brief moment. But for the moment, I just want to be as simple as possible. So it's massless scalars and gravity. And I want to compute the leading order quantum gravity contribution to the 4-scalar vertex. And the whole philosophy behind this is really I want to learn something about the general analytic structure of this thing. So I have to simplify the setup as much as possible, but not so much that I don't learn anything non-trivial. So this is kind of the kind of thinking that is behind this, behind choosing the truncation. So this is the action that I'm considering, right? So there's, as promised, an Einstein-Hilbert term. I will put the cosmological constant to 0. There are 2 kinetic terms, no wave function renormalizations, no anomalous dimensions. And then there's this particular 4-scalar interaction. You see that there are derivative interactions here, so I'm also imposing shift symmetry. Just as I said, maximal simplicity is my goal here. You also see that I pick particular kind of contraction of momenta here with a traces projector. This is just what comes out of my computation. So I kind of, using that already here to set up the stage. You also see that I put an E here to the action and also this form factor indicating Euclidean signature for now, which already tells you maybe that eventually we might be able to recruitate this result. Because if you have it analytically, you can check the complex plane and then you can see whether you can recruitate or not. Very good. In terms of scattering, why is this term important? Well, it really tells you what a simplified version of the contact term is for scalar scattering, right? So if you consider the gravitational scattering of scalars, there's a mediated diagram where you need the graviton propagator and the scalar graviton vertex. And then there's the contact term, and you need, the fully momentum dependent form factor here for this contact term, and this is an approximation to it. So if you would go on and look at scattering, this would be one ingredient for this. And in the paper, there's a little bit of discussion there. Okay, so once again, to tell you some of the technical choices that I'm doing, once again, I'm neglecting the cosmological constant. I'm using the harmonic gauge. This is just to simplify things. You can do it for arbitrary gauge. Another thing that I'm doing is I use what you could call a quenched approximation. So I will not do any scalar loops. I only do gravitational loops. And this turns out that this reduces the flow of the 4-point function to exactly this diagram, right? So you have two 4-point vertices that come out of the kinetic terms of the scalars, one for phi and one for chi, and then graviton propagators going through the loop. I'll also model the flow of Newton's constant in this way. So very simple model, which as far as I found goes back to this paper by Alfio and Martin. And then in the second paper was shown to be a very good approximation in a rather sophisticated approximation of the free graviton vertex. So you can see it as a model, but it is also a model that is kind of shown to be rather accurate in modeling the k-dependence of the coupling. So I take this as an input, once again, just to simplify my life and not having to also compute this from scratch. So this is the setup. And the final ingredient for the setup is really what makes this all possible. That's the regulator choice. I'm using this specific exponential regulator, which will eventually allow me to compute all the threshold integrals analytically, even with an external momentum. So there's a little bit of, if you want, black magic to do this, but in the end, if you understand some basic or standard tricks, it's rather straightforward. So with this regulator, it's really, really nice and possible. Good. So far for the setup, let me jump right to the beta function for this form factor f. So now I'm using a small f just to indicate that I'm looking at the dimensionless version, which you also see in the canonical terms on the left-hand side of the flow equation. So you don't only have f dot, but you also have a term coming from the mass dimension, minus 4f, and then a term coming from the mass dimension of the dimensionless momentum squared, z is p squared over k squared. You get the second term, so a derivative with respect to the argument. And the right-hand side is really the diagram, if you want. So you see it's proportional to g squared, and then some relatively simple momentum dependence, right? So you get a 1 minus exponential of minus z half over z. This is completely regular, of course, at z equals 0, but also at z infinity, no pose whatsoever. Good, so it's really as simple as that. You sit down and you can derive this rather simple flow equation. At this point, I want to note that the beta function is quadratic in G, right? So there are no cubic terms or higher. This comes just from the simplicity of the approximation. I'm throwing out all anomalous dimensions here and all kind of corrections to vertices or propagators or whatever. So it's really the leading order contribution if you want. But just keep this fact in mind that it's quadratic in G. Very good. Now you sit down and you want to solve this differential equation in two variables. And turns out this has a unique solution if you impose some regularity conditions, right? What are these? Well, you first want to assume your regularity at finite k and finite z. This fixes basically the homogeneous solution of this. And then you want some kind of fixed point scaling as you send k to infinity. And this fixes all the rest of freedom that you have in choosing the solution of this differential equation. You can also arrive at the same result that I will show to you in a second by a standard fixed point analysis. So if you want, you set f dot to 0, you solve for the fixed point solution. Once again, you will get a free integration constant. That one is fixed by regularity. And then you look at perturbations, you find all perturbations are irrelevant for this function. And then connecting to the full solution is unique. And I think there's something in the chat. No?
Yes, there's a comment by Alfio in the chat. Alfio, do you want to speak up?
Sorry,
Or
I can't
like,
read the chat.
yeah, so maybe Alfio can.
Yes, just saying that, hi, Ben.
Hi.
In the right-hand side, you
Yes.
basically are not considering the flow of the non-local term. Because, I mean, in general, I mean, that's the whole problem. So I understand that to make progress one cannot do that, but then we have to be careful to come to conclusions like, okay, the k equals 0 limit does not exist or exist, because the real problem is to be consistent right hand side and left hand side. We have done that with the 1 over box in a consistent way with the vectoric equation. It was already a nightmare, and not only I mean, it's not always the case that you can get k equals 0, but in that case, it was possible to get the k equals 0. So in some case, one can get a consistent approximation where you keep the same thing on the right hand side and the left hand side. But if you are not consistent, then we have to be a little bit careful then interpreting the results.
No,
That's
I completely see your point, but I'm in a setup where I do not expect, at least at finite k, any non-localities. I'm not putting in non-localities, so I do not expect that at finite k I get out non-localities because everything is kept by the regulator. Okay?
I don't understand why you don't expect, but I mean, in principle, if you do it, if that is a very general function of z, you might immediately run out in non-localities. I mean, you are truncating a huge functional space, imposing something which might not happen in the follow. You might immediately generate a log of z
But I don't.
just
I
through that
computed the
equation
flow.
of something like 1 over z, which is immediately will create a tremendous problem. You will not be able to compute the trace on the right-hand side in a consistent way. I'm just saying it's not wrong. I'm not saying it's wrong. I'm not totally sure it's we. I mean, of course, it's the best we can do at the moment, but that might not be. We have to be careful in driving conclusions out of this.
For sure, but let's say, let me take the stance of trying to understand whether the derivative expansion can work at all. And then the assumption as well, or the first result is I computed the flow, right? This is the right-hand side, and the right-hand side is finite. You agree, right? There's no poles. There's no pole at z equals 0 because the numerator also goes to 0. So this cancels, and there's no.
Actually, I fully agree with you as long
Good.
as we deal with local expansions. The moment we
Okay.
get something like that, I think that the derivative expansion is probably not a very good choice. But I mean,
Yes.
mine was really only a comment. It's not real critics, and so please take it as just a
No.
comment
So
to clarify, let's say, that the limits of this type of exercise of calculations. That's it. The
of
only thing.
course, but I also think that at this level, I mean, the flow tells you it's local. If you put in something non-local, you've chosen something weird for your homogeneous solution, if you ask me.
Okay, maybe. Let's discuss. Okay.
Yeah, but we can discuss this later. So I also think
Yes.
this is
Yeah,
maybe an issue of
definitely.
this particular truncation because I do not take into account the feedback on the right-hand side of this form factor, and then you would not probably run into these issues because then you have a nonlinear equation, and then it's not so easy
Oh,
to.
yeah, I know.
So,
It's
but for
already right, quite complicated at this level.
yeah,
Okay.
good.
Thank you.
Yeah. Okay. So coming back under all the assumptions that I spelled out, you get a unique solution. Unique solution looks like this. It's a little bit messy, but let me guide you through it. The first line is basically just the right-hand side of the flow dressed with some k-dependent prefactor. Now this capital Gn is really the infrared Newton's coupling. So it's really the physical value that you would impose. G star is the fixed point value of Newton's coupling. And then the second line is a little bit the kind of non-trivial part of this whole function. And maybe the interesting bit is this difference of incomplete gamma functions, which depends on combinations of dimensionless momenta and Gn times k squared. Okay, so this is under the assumptions, this solution to this flow equation. So let's analyze it a little bit. So the first thing that you will notice if you analyze it is that this function is analytic for all complex dimensionless momenta, as long as k is positive. For k to 0, you will have to eventually go to dimensionful quantities, and we'll discuss this in a moment. But as long as k is positive, this is an analytic function, which tells you, at least in the setup, that the derivative expansion works for k positive. So it's really only the limit k to 0 that where something can go wrong. Yeah, for k to 0 specifically, you have to switch to dimension-full quantities again, because you see, well, for sure, the first line will just go to 0 as k goes to 0, and the second line as well. So then nothing interesting happens for the dimensionless version of the form factor. Very good. Before we go to the k to 0 limit, let me just briefly discuss the fixed point. So you take the k to infinity limit, and you find a very simple function. It's basically exponential and some rational bits. And it depends obviously on the fixed point value of Newton's coupling. So what you also find is that the infrared quantity, so the dimension for Newton's coupling, drops out of the fixed point form factor, as it must, because it's an infrared coupling, infrared quantity, so it cannot appear in the fixed point solution. Very good. Once again, this function is analytic. You can write down a Taylor expansion that converges in the entire complex plane. And as you might expect, this is basically an exponential. So everything good here. At large arguments, this function drops off like 1 over z. And if you're interested in the plot, it's very boring, right? So it's basically, well, as you expect, it's something finite at z is 0, and then it just falls off to 0 as z goes to infinity. Very boring, if you want. Okay, so the more interesting limit is the k to 0 limit, and for that we have, as I said, we have to switch to dimension-full quantities again. So we look at the dimension-full form factor of dimension-full squared momenta. How do we do that? Well, we multiply the dimensionless form factor by the corresponding power of k to reinstate mass dimension, and we really have to switch back to dimension-full momenta in the arguments. And then we take the k to 0 limit, and we get to this function. So what you find is essentially an exponential of p squared times one of these incomplete gamma functions. Now, I'm not sure how familiar you are with incomplete gamma functions, so let me plot it. And you realize, well, I have the analytic form of this, so I can plot it on the whole real line. So even negative p squared. So we are not strictly Euclidean anymore here. Good. And what you find is you get a real part and an imaginary part. The imaginary part is 0 for positive p squared. So this is the Euclidean branch, which is good because there should not be anything imaginary for this part of the real line. You see that the form factor is negative. It still falls off like 1 over p squared for large arguments, but at p equals 0, there will be a logarithmic divergence. I'll show you the analytic form in a second. In the negative p squared branch, you also see a 1 over p squared fall off, but you see a branch cut here, so a finite imaginary part. And I'm saying branch cut because really, if you look now at the complex structure, so the function in the entire complex plane looks like this. So the color code is really the phase of the form factor, goes from minus pi to pi. And then the size here, the z-axis, is the absolute value of the form factor in Planck units. And you see that really the only kind of feature that you have is a branch cut that is indicated by this black dashed line on the negative real axis. So observation is this function is analytic except for a branch cut on the negative real axis, which means, well, I can do a Wick rotation. So I can actually use this function for scattering. Great. And it has exactly the right branch cut that you expect from a massless theory. Also great. Good. But once again, this is a direction that I don't want to discuss into too much detail today. I do see a hand. Alfio?
She told me, sorry, not to bother you
All
again.
good.
I mean, this is, this is a form factor.
Yeah.
Okay. How can we trust? I mean, how can we give any sense to this imaginary part being Euclidean, what we are computing?
No, so the point is, strictly speaking, I've computed the flow on the positive p squared, right? So this is where the flow equation works. And
Okay.
right? But now, since I can compute
Okay.
this
Now I
whole
understand.
function analytically, I can do the Wick rotation because I already know the analytic continuation of the function. Because
Okay,
this is the
yes.
function. So
Very good, very good, very good. It
it's the
wasn't
same
clear.
as you did with the propagator, just that I don't have only numerical data, but I have
All clear, Ben. It wasn't clear.
yeah,
Yes. Very good.
great.
Thank you.
So it's exactly the same procedure if you want. Very good. There's a few nice features of this form factor. The first thing that you notice if you look sharply at this is what I might call scale transmutation. So notice how every occurrence of p squared, so in the exponent or also in the incomplete gamma function, is accompanied by a factor of gn. So all momenta are measured in Planck units, and this is kind of expected from EFT, right? But also this is in a sense funny because remember the beta function was quadratic in Newton's coupling. So what you effectively get is all the factors of k squared in the k to 0 limit are transformed into factors of gn. And it must happen like that because at k equals 0, nothing, so k cannot make things dimensionless anymore if k is 0. So something else has to pick its place, and in this very simple case, it's Newton's coupling. And if I maybe go briefly back, you can actually see this in the function, in the full solution. You have the first line where the argument is just p squared over k squared. This will vanish basically in the k to 0 limit. But in the non-trivial bit, where the incomplete gamma function is, you see that you have a product of gn times k squared times z. Remember, z is p squared over k squared. So this is really just gn times p squared. And this is what I mean with transmutation. Same thing for this a bit more non-trivial structure. Here it's a little bit more obvious that something non-trivial is happening. So we have a g star times z, which does its stuff. And then here's the transmutation factor if you want, which I find really nice. So this answered some questions that I had for quite some time, how you can have beta functions that are, for example, quadratic, but then you get really non-perturbative results in the coupling. Clearly, this is a non-perturbative result in Newton's coupling. Okay, now for the analytic structure. So you can expand this function in powers of p squared. However, it's not a Taylor series. So this you can see here. If you want the coefficients are not constants, but they also have a logarithm. So this is exactly why you have a branch cut on the negative real axis. So that's the branch cut of the logarithm here. And if you look sharply, the logarithm pieces just sum together to form an exponential. So this is exactly an exponential decay here times a logarithm. Very good. And here it stares you in the face why a derivative expansion for the form factor cannot work at k equals 0, right? It's this logarithm that tells you, no, I'm not a Taylor series. I cannot be expanded in a derivative expansion. So this is really the reason why the derivative expansion must fail in this limit, in a strictly speaking, right? So we saw that at finite k, everything is fine, but if you take this limit, something must go wrong. And we'll analyze in a moment how bad this is and if you can save the derivative expansion after all. A nice side fact that I find interesting is if you now consider this whole bracket to be the coefficient of the p squared to the n, this coefficient runs logarithmically. So this is kind of giving a meaning or more sharp meaning of what standard logarithmic running means in terms of a form factor. And it also tells you that in terms of these couplings, so if you really, once again, take the brackets as a coupling that is running, these do not go to finite values at high energies. And I think I see another comment in the chat. Can you please speak up?
It's again by Alfio. Alfio, please go ahead.
Just a comment that, I mean, these two limit, the k equals 0 and p equals 0, I think they do not commute.
Yes, that's what I'm saying.
So that's the problem. That's so
Yes.
it's not that the real expansion does not work. If you do, depends on how you define this limit. That's the point.
Let us go into the details, why I say it must fail, and let me quantify how it fails. Okay?
So sorry,
Yeah.
can you repeat how you go from the formula with the gamma function to the last formula? So you are expanding the gamma function, right?
You mean from basically this full solution here?
No, in the last slide, like the very last step.
Here.
Yes, from this, the one on the top right to the one in the center.
Exactly. So this is just, if you want this, the incomplete gamma function
Yes.
times the exponential has a representation that is convergent everywhere in this form. So you can get it can get to there with
And the variables is g p square over g star, right?
exactly. Yeah.
Okay.
So you see that also here in the exponential and in the incomplete gamma function, this is the kind of true argument if you want. So
Yes.
it neatly comes into packed into this factor.
So the
But yeah,
variable is p, because
a priori the variable is p, but p is dimension 4, so you need a dimensionless
okay. Thank you.
quantity. Yeah, but if you want, yeah, this is something like a Taylor expansion, just that I would not call it a Taylor expansion because it has a logarithm.
Okay.
Good. Now, I'm doing the time. Let me actually skip this. That's not so interesting. So let me come to this question of really exploring how badly or how not so badly the derivative expansion fails. So maybe we can actually still use the derivative expansion to get the right limit if we do some clever subtractions. Why am I saying this? Well, let's, for the sake of argument, insist on a derivative expansion. So let's insist that we can write this function f as a Taylor expansion. And let's see if we can find beta functions for the Cn, k, solve these, and then somehow take the k to 0 limit and see if we can get back to the full solution by subtracting offending terms. So it's making the connection to the motivation if you want. I want to see the 1 over k squared terms. Good. So you sit down, you can derive the beta functions, you can derive the solutions for these. It's not super interesting, but it's just to say you can actually compute all the details here. So these couplings, they are essentially hypergeometric functions of k squared. And then once again, for finite k, this agrees with the full solution. For finite k, you can resum the series and you get back the result that I showed you. But now for the limit k to 0, we once again have to convert to dimension full quantities and take the limit. And here we see what goes wrong, right? So I show you the first three coefficients, that's C0, C1, C2, and we're taking the correct power of k to make it the right mass dimension and take the k to 0 limit. First thing you see is, well, you see logarithms. The logarithms are not so bad, actually, because they really correspond to the physical logarithm, so log p squared. We see log k squared, but we should get log p squared, so these are maybe not the offending terms, but for sure, the 1 over k squared here, and the 1 over k squared here, and 1 over k to the 4 here are really offending. They do not really correspond to anything reasonable in the momentum-dependent solution. So let's maybe entertain the idea that, well, maybe we can just subtract these terms that we really do not want, and that, by the way, also have the wrong power of Newton's coupling, right? So C0 should have G squared, C1 should have G cubed, and so on. And these have lower dimension in G. So let's suppose we subtract these and we identify K by some factor times P, because we still want to keep the logarithm, because we know, well, there should be a logarithmic term, because there is this branch cut that is connected to physics after all. So let's try. Okay, I'm throwing out the red terms and I'm identifying. Good. So I do that for Z0 and I equate this coefficient with the full solution and I get a C, so this kind of proportionality factor of K squared to P squared, and this is e to the Euler gamma minus 1 over 2. So you can find an identification, but good luck guessing it. I don't see any way how you guess an Euler gamma here. So it's nowhere in the beta function that you would guess this from. But okay, let's say you know it, or maybe it's universal, I don't know. Let's make some assumptions. And let's try to use the same identification for the others, so C1, C2, C3, and so on, and compare. And you compare and you find your other coefficients or Wilson coefficients are off. So it's not the right scale identification. So you, once again, to maybe what I did here, I used this identification that fits the value of C2 of the derivative expansion and the full solution. I used this scale identification for C1, and I get a difference for the exact value versus the derivative expansion. And this happens for all higher order couplings as well. So you get a quantitative error here. Now the only other choice that came to my mind would be I set an individual scale identification for each of these coefficients. That works if you know all these values of C, but you, once again, I mean, good luck guessing this. There's no way to, at least I didn't find any reasonable way to fix this. But the learning for me here is, to summarize this, if you do not do the subtraction, the derivative expansion fails qualitatively because you get 1 over k divergences. You can subtract those to only be left with the logarithms. The logarithms actually come out correctly, but the constant bits, or really the Wilson coefficient, you get a systematic error that you cannot quantify within the derivative expansion. And it is of order 1, as you can see. So maybe even a bit larger, but order 1-ish for all these coefficients. Okay, so maybe in the last few minutes, let us briefly talk about this logarithm again. So we understood that the derivative expansion has its issues, but maybe you're a little bit worried about this logarithm, right? Because now you look at this, and you realize the logarithm really dominates the small momentum regime, right? So you go to small p, and small, what is small? Small in Planck units, so not so small after all. And for this form factor, in this regime, so p squared smaller than Planck mass squared, the logarithm dominates the coefficients. And this is not what we see phenomenologically. We do not see large quantum gravitational logarithms in standard model couplings. So if this pattern persists in massive theories, we have a problem, because this will overshadow everything, and then I'm not sure what we are doing. So we need a mechanism that kind of contains this logarithm, for example, in the standard model, so in a massive theory. But in massless theories, I do not see an immediate way to kind of screen this, because, well, massless theories don't have any other mass scales, right? Good. So for this, let me now introduce mass terms into the whole setting. So I basically repeat the same analysis. The things that I'm changing are I introduce mass terms, so I'm breaking shift symmetry, which also allows me to look at a somewhat simpler form factor here. So it's really just a phi squared and a chi squared and a different form factor F4. But otherwise, completely same setup, completely same flow, completely same approximations. Of course, I also have to make approximations for the masses, for the masses, I'm assuming that they do have a fixed point at small m phi star or m chi star. And in the infrared, they have some free parameters, so the physical masses m phi squared, m chi squared, and I can tune them as I want. So I get two more parameters, but still I have the full thing under control. I can compute everything and do the same analysis. So let me skip all the details and focus on exactly this limit of k to 0 and investigating whether the logarithm a still appears and b can be contained. So I'm taking now the physical form factor, so this is the k to 0 limit of f4, and I look at the small p squared behavior. So if you want, this is kind of, if there would not be this logarithm, this would be p squared is 0, so the constant term. But the first thing we see, well, there is a logarithm. So the gravitational logarithm is still there. But now there's also other terms, right? So there are terms in the first line where you have in the very first term only fixed point values. So this is kind of order 1. Then you have a second term which is roughly gn times m squared. So this is one Planck mass suppression by 1 over m squared. And then the term with the logarithm and some other constants, which is yet again suppressed. So it's mass to the 4 over Planck mass to the 4. And this is really what kind of effectively saves us here, because now you can compare when is this logarithm the dominating bit in all of this expression. And you plug in something like, I don't know, Higgs mass for the masses, order 1 fixed point values, and you find a p squared, which is this ridiculously small number where the logarithm contributes the same as these constant bits. So this is meaning to say that in massive theories, there's practically no issue with these logarithms because they're just so suppressed that you don't really care effectively. And this is also what can save you for the derivative expansion in such theories, because what you most likely, one has to do the exact computations in the specific model, but what you most likely observe is you see a plateau effect. So no running with k anymore at roughly the mass scale that you have. And then in the very, very, very deep infrared, where k is roughly of this order, you see the logarithm kicking in. So effectively, in such theories, you can do a derivative expansion, maybe, I'll come to the maybe in a second, and get away with it. Very good. Now, the obvious question here is, what if the first two lines are 0? So if you're starting with a fixed point where the masses are 0, then you're kind of back in trouble zone. And then you have to look at whether there's any other mass scale or anything else in your system that can save you. But you kind of need an order 1 number or something that is not Planck mass suppressed. And generally, I think in the standard model, you should expect something like this. But there must be a mechanism that kind of suppresses the logarithm. And generally, we expect this to happen. Very good. So maybe one last thing before I summarize. You could ask the question now, let's take a purely massive theory, so no quantum gravity fluctuations, but just take a scalar field that is massive and check whether the derivative expansion works for this, for computing beta functions of gravitational couplings. I want to once again do the simplest possible case. Now I'm doing one loop. Okay, I take the Wetterich equation, I take a free massive scalar field, and I solve the Wetterich equation at one loop and look at the contribution to gravitational couplings. So this gives you this trace log formula, of course. So difference at some cutoff lambda minus the effective action at k gives you a trace log of the ratio of propagators. Very good. Now you might naively think that, well, everything is gapped by the mass, right? Because it's finite. So a derivative expansion should work. It should, but it doesn't. So for definiteness, look at the R² form factor. So and you can compute this whole thing. For definiteness, I just picked the R² form factor, used the non-local heat kernel, and then I sent k to 0 and the cutoff to infinity. So kind of really one loop with a cutoff. And I get what you would expect from EFT. I get a logarithmic divergence for the pure R², and then I get power law corrections, delta over m² to some power, but they are all finite, as you expect. Very good. So this is taking the full non-local heat kernel, so the momentum-dependent form factor, taking k to 0 and then expanding. So this is the correct order if you want. So first doing the k to 0 limit and then expanding. And this gives you a nice Taylor expansion, no log of p². Now you do it the other way around. You first expand in p² and then take the k to 0 limit, and you run into trouble. So you get the logarithm right, okay, but already at the p² over m² level, you get the wrong number. It's 672 and not 336. And then at a higher order, you get a 1 over k² divergence. So even in this rather simple case, you run into technical trouble if you do a derivative expansion. And if you dig deeper where this comes from, it's really coming from the fact that your kind of p² derivatives hit the regulator. And if you're at finite k, so you get contributions from derivatives of the regulator, and if you send k to 0 afterwards, you get these contributions. Whereas if you take k to 0 first, and then take derivative with respect to box, you don't see that. So once again, k to 0 limit and derivative expansion do not commute. So if you take anything away from this talk, it's really be very careful if you're studying the k to 0 limit in gravity. Because even in cases where you think everything should work, it might not. Very good. So to summarize, I think this shows that you cannot really avoid some kind of momentum dependence. Also, curvature or field dependence should work in a similar way. I didn't go into the details, but I think you need some, if you want, physical quantity that can kind of gap these logarithms and that you do not expand in, if you want to study gravity in the strict k to 0 limit. Effectively, you can work with a derivative expansion if you have massive fields. They might gap the offending terms, but once again, it might not work in all cases, for example, for gravitational couplings. So there's a little bit of a question mark there. So again, maybe the most important thing to take away is be careful if you're doing these computations. The positive note is maybe for UV fixed points, derivative expansion works great. And maybe the last point here, what I find really nice is that you can get some momentum dependence analytically, and I'm working on different directions here, so definitely watch out for more. And with this, I want to thank you for your attention, and I'm looking forward to more questions.
All right, thank you, Benjamin, for a very nice talk. And